Okay, can everyone hear me? Perfect. So I'm here to talk about a local continuity bound for the entropy of finite distributions. So I'm at Hanson, supervised by Nilanjana Data. So finite distributions are very simple. We have a set omega, which has d elements. We can imagine d is very large if we want to be high dimensional. And we consider probability distributions on omega. So it assigns a non-negative value to each entry of omega, and the values sum up to 1. And then we can define the entropy by the formula given here. And it's a very important measure of information about this probability distribution. So it measures how much we can learn by observing outcomes of this distribution. So the entropy is minimized on a probability distribution that has the value 1 for one of the entries of omega and 0 for all the others, because when we observe samples from this distribution, we don't learn anything. It was always going to give us a certain element. And the entropy is maximized on the uniform distribution because we can learn the most, because we're the most surprised by whatever outcome we get. So why do we care about entropy? So it's a fundamental quantity. It has an operational characterization by Shannon's source coding theorem. So we can think of the entropy as an asymptotic optimal lossless data compression rate. So if we want to compress data without losing anything, and we have some asymptotic sequence of data that we're getting from a particular probability distribution P, then the optimal rate we can compress this data is the entropy, H of P. It's also related to other quantities. For example, it's the conditional entropy when we don't condition on anything. It's just the entropy. And it's also the von Neumann entropy of a d-dimensional quantum state, because the von Neumann entropy of a quantum state is the regular entropy of its eigenvalues, because its eigenvalues form a probability distribution on omega if it's d-dimensional. So that's really where my interest comes from and where the title comes from. But I actually won't talk about quantum mechanics in this talk. So the other element of the title of my talk is continuity bounds. So for a very simple example, I'll plot x squared, and I'll consider continuity bounds. So we probably all know what continuous means, is if two input points are close together, two output points are close together. But we're interested in a very particular thing here. So for a continuity bound, we imagine we don't know the values of x or y. We just know they're in the interval 0, 1, and they're within epsilon of each other. A continuity bound tells us that f of x minus f of y is less than 2 epsilon. So of course, this is the definition of continuity, but we care about the fact that it's actually 2 epsilon because we might need to use this number in some sort of application. So it's not just a limit. A local continuity bound is where we also know the value of x. So we have local information, and we can get a tighter bound. So by a simple computation here, we can figure out that f of x minus f of y is bounded above by x plus 1 times epsilon. So if we happen to know x was 0, for example, then we would just have f of x minus f of y is less than epsilon, so it's a tighter bound than 2 epsilon. So there already exists a continuity bound for the entropy called the Odenat fairness bound. And I won't go into the details, so it's a fairly simple formula. And so if we think about what the Odenat fairness bound tells us, this is a continuity bound for the entropy. If we have two distributions and we don't know what they are, all we know is that they're close together, then this will tell us how far the entropies can differ. But what might be more useful for us is a local continuity bound, where we have some unknown distribution P, but we do know something about it that is close to a known distribution Q. And then we want to use the information we have about Q to come up with a better bound on the entropy of P. And so that's what I'll work for here. So there's a very simple way we can come up with a local continuity bound, which is really sort of a trick of the definition. If we want to upper bound h of p minus h of q, where q is the known distribution, we can bound it above by the maximum over all distributions p that are close by in our distance measure from q. And we can do the same thing. We want to bound the absolute values. We can do the same thing with the minimum for h of q minus h of p. And we get this maximum of maximizing over distributions near q of the entropy minus h of q, and similarly for the minimum. And this is a function of q and epsilon only. So it is a local continuity bound, but we haven't done very much because we have to actually figure out what these maximizers and minimizers are. So the idea is to understand the maximizers and minimizers of the entropy over this set of distributions nearby to Q. So I'm just going to invoke the black box of convex optimization here and say that it'll help us find optimality conditions for what these maximizers are for the entropy. And the hint we get is for the maximizers, if we start with the distribution Q, which is ordered as follows on the right, so I just sort of plotted the entries of Q like their energy levels in a physics diagram. And how we want to construct P star, which is some maximizer of the entropy for distributions nearby to Q. And we want to construct such a distribution with maximal entropy. So let's remember that the uniform distribution has maximum entropy over all distributions. So that maybe will help us interpret why we do what we do. What we do is we shrink, we sort of compress the distribution by shrinking the largest entries and raising up the smallest entries. So they'll still add up to 1, and it's sort of more concentrated in the middle, and we leave the ones in the middle alone. And that gives us this P star on the right. And it turns out, if you choose the right ways to shrink it, this is the best you can do. And so we can do other things with the minimizer that you can come to see my poster for. And that gives us this local bound. And so with 500 random choices of Q, it does better than the global bound for each of these choices. And actually, we can prove that generically it does better. But it's more illustrative with this example. All right. Thank you.